So in the last two videos about the ARM2 microprocessor that I'm trying to get hooked up, I showed, well in the first video, I showed setting up a two-phase clock and showed the CPU running based on that two-phase clock with LEDs connected to the low bits of the address bus so that we could see that the CPU itself was doing something. And then in the second video, I talked through what all of the different pins do on the ARM2 processor and on the breakout board I made. So what I really want to do in this video is actually get this hooked up to some memory. In order to do that, we need to talk a little bit about the bus timing, because although I talked through what all of the pins do last time, the timing of them is also more complex than it is on the 6502 and really important to understand. So the datasheet contains this massive timing diagram which shows the relative timing for all of the different signals on the CPU, which is great and all, but it's pretty hard to see what's going on in there in a lot of cases because they've had to put all of the different possibilities and eventualities onto one diagram. And in fact I think there are some things that are kind of left off the diagram as a result. So from looking at that and from looking at some other diagrams elsewhere in the datasheet and reading the datasheet, I've come up with this somewhat simplified diagram which shows just the signals that are most relevant for what we need to do here. So from the top down we have the two phases of the clock, phase 1 and phase 2. We have the M request line, the memory request line, which goes low when the CPU wants to access the memory on the bus. The timing of this signal is also the same as for the sequential access signal. We're not actually going to use the sequential access signal though, so don't worry about that one. On the next line down I have the timing of various other signals, which includes the read versus write signal, the byte versus word signal, the opcode signal, which again we're also not going to be needing, and the address bus. And finally at the bottom here I have the timings for the data read and data write. And what this means is that during a read cycle, the data read line is relevant, and this shows the portion of time during which the CPU requires consistent data to be presented to it on the data bus for it to read from the memory. And the data write line is only valid during write cycles, and it shows the portion of time for which the CPU will be putting valid data onto the data bus for us to write into memory. So most of these signals are very similar to ones that we've probably already seen on a 6502. Let's talk about what the differences are. And the biggest difference is pipelining. So let me highlight one of the bus cycles that this diagram contains, and we can see which bits of data contribute to what happens during that cycle. I'm going to do this based on Phi 2, because like with the 6502, the portion of time when phase 2 is high is broadly speaking the time during which the CPU is accessing the bus. That could be relevant later on if we do some video access as well, because the portion when Phi 2 is low is obviously the best time to be doing that. So I'm just going to highlight this second cycle that I've included in the diagram here. And during this second cycle, if it was a read cycle, then this block of time would be relevant for the read. That's the block of time that shows when we need to make sure that the memory is outputting to the data bus so that the CPU can read from it. And if it was a write cycle, then this block at the bottom would be the relevant block for the data bus access. And that means that the CPU would be presenting data for us to write to memory during that period. Now the CPU tells us actually an entire cycle in advance whether it's going to want to do a memory request during the next cycle. So the memory request signal is relevant for this cycle during this period. And again, notice that that is actually overlapping with the previous cycle. And the read versus write, byte versus word, and address lines and opcode line are actually containing the right data for this cycle during this period, which is somewhere in between. So that's a bit awkward. In case it makes things clearer, let me also draw the previous cycle on in a different colour just so that we can see how that lines up as well. And I've run out of colours, so I won't use another colour for these periods over here, but this period and this period would actually be part of the following cycle. So as you can see with the pipelining the way it is, at the time where we need the memory to be outputting data for the CPU to read, the address is no longer on the bus. In fact, neither is the signal that tells us that we should be reading rather than writing, nor the signal that tells us whether we should be reading a byte or a word. And finally, the signal that tells us that we should be doing anything at all is long gone from the bus. It actually ended way back here. So there's no point in time when all of these signals are valid, and we're definitely going to have to latch something. One thing that helps us out a bit here is the address latch enable pin, which I did describe the meaning of in the last video. But this will show hopefully why that's important to have. So what I've drawn on the bottom here is a second version of the address bus, but I've delayed it. I've delayed all the transitions on this, and what I've done here is I've drawn this as if the address latch enable was being driven by phase 1, something like that. I think connecting phase 1 to address latch enable will essentially provide this behavior. And if I now draw on the colors for these different addresses, you can see straight away that that's going to be much more useful to us, because now we have this period at the end of phi 2, the trailing edge of phi 2. We simultaneously have the period when we need to be providing data to the CPU, the end of the period where the CPU is providing data to us, and the address still being valid on the bus. So that's really helpful, and essentially this address latch enable pin means we don't actually need to latch the address. But we do still have problems with the memory request line and the read, write and byte word lines, which are all not valid at that stage, and we're going to have to do something about that. The read, write and byte versus word lines, we could latch them on the rising edge of phi 2, because they are still valid at that point, just about. The memory request one, we could latch on the previous phi 2 rise, but that could get complicated, because by this point we need to be latching the next one in that case, and we still haven't done the bus cycle for this iteration. So I don't really want to do it that early. The falling edge of phi 2 or the rising edge of phi 1 might be good times to latch the memory request line. And in fact, if I'm latching anything at that point, I might as well latch the read, write and byte word lines as well at that stage. So I think that's probably what we should do. Take the rising edge of phi 1, use that to latch all of these, and then just remember that, carry them forwards until the trailing edge of phi 2, when we're going to be done with all of our reading and writing at that stage. And what that means is that when we've done this latching, we're basically going to be able to treat the phi 2 high period just like we would on a 6502. When we're reading data, we can just use that period to tell the ROM or RAM to start outputting data, and it will definitely be fine by the end of the cycle that way around. And when we're writing data, we can again just tell the RAM to accept new data for that entire period, and it only really cares what happens at the very end. But the CPU is going to keep that data valid throughout. And let me also show you this diagram from the datasheet, because this one I found very interesting and illuminating, but also quite hard to read. This diagram shows 4 different bus cycles. This diagram shows 4 different types of bus cycle. And this kind of explains why they went to the trouble of pipelining these signals so much. The most interesting ones are the N cycle and the S cycle. The N cycle represents a non-sequential read from dynamic RAM, and the S cycle represents a sequential read from dynamic RAM. And armed with what we just went through on paper, hopefully you can see the memory request and sequential access lines having their values set basically a whole cycle in advance, and you can bear that in mind when you're looking at this diagram. And what you'll see is that when the sequential access line is low and the memory request line is low, that starts the N cycle, or that means that the next cycle will be an N cycle. And during that N cycle, you can see that the memory hardware is controlling the row address strobe and column address strobe lines, and it has to do a row address strobe in order to latch the high bits of the memory address into the RAM. And that takes some time because it has to wait for a while after that before it does the column address strobe to determine the final address to read. You can also see that the address bus is changing during the actual memory access, because by that time the column address strobe has already been sent. And that means that the RAM no longer cares what's on the address bus, it's already latched the value internally. And you can also see by that point the CPU is already telling the memory controller whether the next cycle is going to be sequential or not. So notice that it is telling the memory controller here that it is going to be a sequential cycle next, and as a result the memory controller can keep the row address strobe active so that the memory continues to read from the same bank of RAM. And that means that when it comes to the sequential cycle, it doesn't need to do a whole RAS cycle from scratch. It can just go straight to the CAS cycle, provide a new address, and read or write new data. And that's why the sequential cycle here is shown much shorter than the non-sequential cycle. And in fact, the mechanism that you have to use for this is essentially to stretch the clock if the RAM needs more time. And in the Acorn RISC machine, the whole design was based around the memory controller actually controlling the clock. The CPU was entirely clocked from the memory controller, and this two-phase non-overlapping clock was all output from the memory controller. And whenever it needed this kind of thing, it would just pause the CPU for a bit. The remaining cycles shown on this diagram are, I think, an internal cycle, they call it, which is when the CPU is doing some internal work and doesn't need access to the bus at all, and a coprocessor cycle, which is where the CPU is reading or writing to or from the coprocessor. And again, it doesn't need the memory to be on the bus for either of those, so the memory request line is high for both of those. But that also means that during these cycles when the bus isn't being used, the CPU does provide the address again really early through the pipelining, and that means that the next cycle can always be a sequential cycle because the CPU has provided the address so early that the RAM hardware has had plenty of time to spin up and get ready to provide that address during the internal or coprocessor cycle when the bus wasn't needed by the CPU. So hopefully that kind of illustrates some of the steps that the Acorn engineers took to try and maximize the use of memory bandwidth here, and a lot of this system was designed around that goal of making the best use of the memory bandwidth. And again, having the memory controller in charge of all the timing of the system is a big part of that, I think. So now that we understand how to set up the bus timings, let's have a quick look at how we can set up the actual interconnections between the various units here. I left a comment at the end of the last video asking if anyone had any particular ideas for how to connect up 8-bit EEPROMs to a 32-bit data bus. So I suspect this is how the ARM designers intended the setup to work for ROM. It certainly seems likely given that the original Acorn RISC PCs and Archimedes had 4 sockets for the OS ROMs. It would make a lot of sense. It's probably the simplest way to do it. What we have here is all 4 ROM sockets have the same address pins mapped to them. That's address pins 2 upwards. I put 25 here. They may not have all 25 pins connected. But all 4 ROMs receive exactly the same address on any address cycle, on any bus cycle. The difference is that the 8 bits of output from ROM 1 fill the bottom 8 bits of the data bus. The 8 bits of output from ROM 2 fill the next 8 bits. The output from ROM 3 fills the next 8 bits, and ROM 4 fills the last 8 bits. Essentially that means that the first byte within the 4-byte word comes from ROM 1, the second byte from ROM 2, the third byte from ROM 3, and the fourth byte from ROM 4. And this means that when we write these ROMs, first of all we're going to need 4 separate ROMs. There's no way we could run the system with any less than 4 ROMs this way, because if we did, only the bottom 8 bits of each byte would get filled in, and that's not going to work because all the ARM instructions are 32 bits wide. So we need all 4 ROMs, and indeed we also need to take our program and split it across all 4 of the ROMs. We need to send 1 byte to each ROM in a kind of interleaved sequence. So that's not too hard to do. I mean, we can write programs on the PC side to take the compiled code and work out what the ROM images should be, but it's also going to be a bit of a pain to actually program all 4 ROMs. So this probably is how I'm going to do it first of all, because it is less wiring on the hookup side. But it's going to get old really fast when we actually are changing the code quite a lot, so I'm probably going to migrate away from that at some point. And I thought I'd show some sketches of other designs that I might migrate to. So this one seems a likely contender. The idea here is that there's only one ROM chip, and we just write the ROM image with all of the bytes sequential as you'd expect. Nothing fancy going on there. And again, it receives address bus lines 2 through 25. Then, in order to actually fill in the CPU data bus, which is 32 bits wide, from this ROM data bus, which is 8 bits wide, we actually need to hit this ROM 4 times per bus cycle and capture the 8 bits from the ROM into separate 8-bit D flip-flops here. And then when we have all of the data into all of the D flip-flops, they then feed the relevant parts of the CPU bus. It is a bit more complicated. The mechanics here are a little trickier. We need a faster clock going into this system so that it can tick multiple times per bus cycle. We need a counter, and the counter is going to kind of drive the A0 and A1 lines, which do need to go into the ROM, because the ROM is storing 4 separate bytes for each word from the CPU, so its A0 and A1 lines do need to be fed by something. And we also need to make sure that when we're reading one of these bytes, it goes into the correct flip-flop. So we also have a 137 decoder here. It might use a 138, not sure, but maybe a 137 with 4 outputs from it. So depending on the status of the A0 and A1 lines, one of these 4 goes low, which will cause the corresponding flip-flop to tick. Some of the details I haven't nailed down here are exactly when we enable and disable this 137, because that will also cause some element of ticking to happen. We might need to count more than 4 here. We might want to count to 8 so that there's a bit of clear space between each of the outputs going high. We never have 2 high at the same time. I haven't figured out all the timing for that yet. Anyway, it's an interesting system, and it would allow me to only have one ROM and program it much more simply than with the first system I showed. This is actually simplified by the fact that ROM is read-only. We don't need to worry about the byte versus word modes on the CPU, because when you're reading bytes, the CPU is quite happy for you to just send a whole word anyway. It picks the right bit out of it, and we're never going to be writing bytes to the ROM, so it doesn't really need to know what's going on with the byte versus word line. And finally, I wanted to show this other scheme here, which is somewhat more complex maybe. So at some stage we are going to have RAM in the system, and these bottom 4 scrawlings here say RAM. The use of this RAM is very much based on what we just saw in the previous in the previous diagram, where there was a 137 counter based on the low bits of the address bus, which determines which of the RAM chips are active. This is particularly for byte read and write, or particularly for byte write modes. Again, on read cycles we don't need to worry about that, and on word writes we also don't want to worry about that. We want them all 4 to be active. Haven't really drawn on the diagram how that would work, but what I was particularly thinking about here was having a system where the ROM is actually never directly connected to the CPU. And rather than connecting the ROM to the CPU, what we do is on startup, before we even start the ARM, we run this counter through the entire address space of the ROM, and we essentially drive the bus from the counter with the ROM outputting its current data here, bus transceivers here making that data go through to the individual parts of the data bus, so that just replicates the ROM's 8 bits of output across the 32-bit data bus. Then we have all 4 of these RAM chips are in write mode, so that they're receiving data from the data bus. The addresses all get piped in just like they were coming from the CPU, and the 137 decides based on the low bits of the address bus which of these RAM chips needs to be activated. So essentially what we're doing on startup here is reading the entire ROM and writing it into RAM. And the idea is that we then just run it from RAM. And the RAM is going to have this kind of complex system. But the interleaving won't be a problem, because this circuit will essentially interleave the data for us while it's unpacking it from ROM to RAM. And again, the single ROM chip here will just contain a sort of regular byte stream of the instruction data. It doesn't need to be pre-processed in the same way that we will need to for the first diagram. Anyway, these are some things I might look into in the future, when I get tired of writing 4 ROMs every time I change the code. There is one more idea that I have in mind, but I won't go into that now. Let's get on with things. I'm going to go back to the first diagram, and I am going to implement that with the timing logic that we discussed earlier. So this is the circuit I've come up with. I think this is pretty much what I was expecting from what I went through earlier on. There are 4 ROM chips here, all sharing the same inputs on their address bus. but each one having a separate data bus going to a different portion of the CPU's data bus. They all have their write enable tied high, and the chip selector all tied together, and the output enables are all tied together. And then I've used a combined 8-way D flip-flop here because there's a whole bunch of signals that we want to latch on the rising edge of phase 1. So I might as well put them all through one IC here. And this is a 74HC273. So in particular, the memory request and the read-write line are the most interesting ones at the moment for the ROM-based system. These other ones I've put on here I think are going to be useful for when we add RAM. I don't know, I mean some of them aren't useful at all really, but I thought I might as well put a few more on. And the latched memory requests line is what feeds the chip selects on the ROMs, so they won't do anything unless we're in a memory bus cycle. And the latched read-write line goes straight into the output enable on the ROMs, and this just makes sure that if the CPU is trying to write to memory, the ROMs aren't going to put anything onto the data bus at that time, because if they did, then we'd have the ROMs and the CPU both writing to the data bus, and that's not good. So I'm going to go away and build this up on the breadboard, and I will come back and explain that once I've done it. So here we are with the circuit that I just described and showed the diagram of, built on the breadboard. I think this is pretty much exactly what I showed in the diagram. Let me explain what's going on here. So in the lower corner over here, we have the same clock system that I set up in the first video. And at the bottom center here is the visualization of the bottom bits of the address bus, which I also showed in that video. At the top you can see the 4 ROMs, and in the bottom left here is the 8-way D flip-flop. You can see that the clock input of the D flip-flop is driven from phase 1, coming from the clock module over here. And I've wired the outputs of 2 of the elements of the D flip-flop through to the control signals on the ROMs, and that's just copied across to all of the other ROMs by these yellow wires. And these 2 are the memory request and the read-write signal. And as I said before, the memory request controls the chip select on the ROMs, and the read-write signal controls the output enable on the ROMs. In terms of wire colors, green is for the address bus. So I have 8 bits of the address bus coming all the way down the center here. It's not the bottom 8 bits, I left the bottom 2 bits off because they're pretty boring on this CPU. So this is bits 2 through 9 of the address bus. And that's what will show up on these LEDs. I only wired 2 of the address bus bits to each EEPROM, and this means that they can only see 4 unique addresses. All the other address pins on the EEPROMs are grounded here. You probably can't see very well, but I've used lots of tiny little wires here to tie them all to ground. This is just because I didn't want to do lots of address bus wiring for this video, and that's absolutely fine so long as I keep my program to only 4 instructions. And I've used blue for the data bus, but you can't see very much of that on here. Basically all I'm doing is I'm routing the bottom 3 data bus pins around the side of each EEPROM so that I have a nice block of 8 pins of data bus along the top right of each EEPROM. And I'll wire those through to the ARM CPU using long ribbon cables. What else is there here? The write enables are all tied high. Oh, and I also set up a sort of on-off switch thing over here, so you can see the clock obviously responds when I turn it on, and the lights indicate whether it's on or off. As for the EEPROMs, I have pre-programmed the EEPROMs so that each EEPROM has 1 byte value in all of its locations. So every single memory location is going to show up the same instruction here. Remember that each EEPROM holds a quarter of each instruction, so the low byte of each instruction I think is in this one, then the next byte up is in this one, then the next byte up in this one, and the next byte up in this one. And yeah, all of those 4-byte words for all addresses are going to look exactly the same, so we're just going to run the same instruction in this case. And the instruction I programmed in is a simple jump instruction that hopefully will allow us to see via the visualization of the data bus, via the visualization of the address bus, whether whether the opcodes from the ROM are getting into the CPU and whether it's processing them properly. So it's a very simple test. It's not going to be anything spectacular, but I think it's an important step to see whether this much works, because I've been umming and ahhing about how I want to arrange this bus. So I thought it was worth just going ahead with this one first, and then doing some more umming and ahhing afterwards. I've also wired a lot of ribbon cables and things onto the ARM breakout board here. The address ribbon cable is attached here still, but as you can see, I left the bottom 2 pins off. And then we have 1, 2, 3, 4 ribbon cables of data bus, which are going to go to the ROMs. I have a power cable up here. This is the address latch enable cable. And then various control signals coming from the top of the board here. Oh, and the clock, obviously. So yeah, I'm gonna do this off camera because this is a lot of wires to try and connect. So I'm going to wire that on and come back when that's all wired on and turn it on and see what happens. Okay, well that came out a bit of a mess, as you can see. There are a lot of wires to connect here. But I think I've got them all connected in the right places. You can see the 4 data bus kind of ribbon cables there, going to one going to each ROM chip. There's this sort of grey and white cable that I've put an extension on, goes to the clocks. Yellow and green for power, because I couldn't find any red and black. Address latch enable, the white wire there, is connected through to the Phi1 on the breadboard. And then the black, white, grey and purple are, I think, the byte versus word, read versus write, memory request and opcode signals. I've routed all of those through to the latch down here, even though we're not using the byte versus word or the opcode indicator. And the outputs from the latch, as I showed before, are connected through to the control lines on the EEPROMs, or ROMs rather. These aren't actually EEPROMs, these are NAND flash or NOR flash or something like that, but they work the same way. Oh, and the address bus is also connected through down here onto the green wiring in the center of the board, as I discussed before. So let's see what happens when we turn it on. Well, it's all flashing away. It's a bit hard to see whether it's working properly. It's definitely not counting up linearly like it was before, so I guess that's a good sign, because the program that I put in the EEPROMs is intended to make it jump around memory a bit. I'm going to try slowing that down. Now, in fact, what the program actually does is jumps backwards 4 bytes on every instruction. So I put the same instruction in all locations in the ROMs. So what we should be seeing is the counter going backwards. However, because of the way the pipelining works, it takes, I think, 3 cycles for it to fully execute the branch instruction. So what we're expecting to see here is an opcode fetch followed by a read from the memory location 4 bytes ahead of where the opcode was, and then a read from the memory location another 4 bytes ahead. And these are opcode prefetches for the following instructions, because the ARM doesn't know yet that it's not going to execute them. And then once it's done those 3 reads, we should see it then jump back 12 bytes. And that'll be going to 4 bytes before where it read the first branch opcode from. So we should see it kind of count on the counter here, ignoring the bottom 2 bits. We should see it kind of count up like 0, 1, 2, and then, well, that'll go down and wrap. Let's take a larger number, but suppose it said 10. We'd expect it to say 10, then 11, then 12, and then go back and say 9, then 10, then 11, and then go back and say 8, then 9, then 10, and so on. So we can kind of see what's going on here. I wonder if I can slow it down a bit more. It does look like it's working. I'm worried about going too slow because I'm well below the minimum speed spec for the CPU at the moment. It's not meant to run at these low speeds. So I'm just going to look at the bottom 4 bits and read out the numbers that I see as they come up. It's going to be pretty fast, but let's see how that goes. No, this is going to be too difficult. I can't do that. I think it's working though. Let's see if I can make it slower again, and then I might be able to read along. So that's 1, 2, or 15. Oh, no, it's too quick still. I think that's working though. If you look at the bottom 3 bits, let's say, then that's kind of going 4, 1, 2, 3, 0, 1, 2, 7, 0, 1, 6, 7, 0. Yeah, it is working. I'm pretty sure it's working. So yeah, that's good. That's good to see. So this is obviously a very simple program I've put in there. It's the same instruction in every location in memory, but it is definitely executing that instruction, which means that the ROMs are working, the data bus is working. Yeah, so that's a really good sign. So I'm going to have to think about what to do in the next video. I could take these ROMs out and program something much more elaborate and interesting into them. I've been thinking about making a debug port. This would essentially be something which captures writes to a certain memory location, or maybe just capture all writes, and I could indicate on a series of 32 LEDs at the bottom here what the last value written was, or something like that. Or maybe if I did actually link that up to a proper kind of memory mapped address, then that would be a very simple way to get some output from the CPU. And we could do some programs that do things like, I don't know, count up in the Fibonacci counting up, for example, is quite a simple program, or counting up in primes, that kind of thing. So I might try some of those things in the next video. The other thing on my mind is just that this arrangement of EEPROMs is quite inconvenient, as I said. I've got some scripts now which separate the linear stream of bytes into a ROM image for each EEPROM, so that's not a problem. But it is quite annoying having to take every single EEPROM out, put it in the programmer, program the right image into it, not get the wrong image into it, and then put it back in the breadboard. I'd really like to work around that, and yeah, I explained some ideas for simplifying that earlier on, and I might jump in and do one of those before moving on with more complex programs, because debugging and changing the program when it's wrong and things like that are going to be very tedious with this particular setup I have right now. Anyway, I hope you've enjoyed watching. Sorry, this one's going to be quite long, I think, so I hope that's okay with you guys. There's obviously been quite a lot of theory I've gone through here, and I doubt I'm going to cut very much in the editing, because I think it's all pretty important. And then we have this practical bit on the end as well, because I really wanted to actually get this up and running this weekend, and yeah, and have something to show. And yeah, I'm really pleased that this is actually working, and this is again another indication that this CPU works properly, and also that I understand how it's meant to work. So I'm glad on both those points. And the possibilities are really opening up as to what we can do with this next. As always, if there is anything you're particularly interested in, do let me know in the comments. Any suggestions, any mistakes you see I've made, I'd love to hear about that. Otherwise, see you next time.